Okay, right now that we have just run our first, I should say, stand model in R, and that's the time that essentially that's going to be a good thing if we can just see what we have, I should say, if we have had some kind of a convergence for our model before we just go out to print and take the summary of the things that we needed to have. Okay. But before that, before we just move on, I'm just, in order to just take the summary, we just want to just do some kind of a convergence diagnostics. And that's the thing that I just want to do that, because before we just move on and to build our many different, I should say, submodels into the model that we have done, we just go, for example, to run, I should say, the loop, for example, you just for model validation, cross validation, or anything. That is always just good that to just come to check for the convergence of the model that we just created. In order to just check the convergence, we have to do two things. First of all, for example, what I'm just going to do, I'm just going to come here to just use the extract function, which again, extract function is something that you expect to find it just with the rstand package, which you already installed it in your system. You see, we have the rstand package, which is successfully installed. We have a tick on the left side of the package name, and now it enables us to just use the extract function. If you wonder what arguments you have to just use, you can just press F1. Just open, I should say, the first option, which it comes with the rstand, and see that, oh, let me just take this one away, and see that what arguments that you have to just put inside the, as an argument inside the thing which you have done. Okay, first of all, for the objects that we have to just put, it says that you have to just use a kind of a stand fit, a class of a stand fit. What does it mean, the class of a stand fit? I'm just going to take you back on the previous line, and I'm just put the, I should say, the functions class in the R, and I just put the model A. And now, I'm just going to execute that line by pressing Control Enter. You see that the class of model A that we created, which was essentially the model that we just run it by using the stand function, it says that it's the class. I'm just going to execute it once more. It's a kind of a stand fit class, and it comes from the package which is called rstand. And when you look at this one, as it says that an object of the class stand fit, then it becomes very clear for you that the stand fit that we are just going to use here as a model, it's going to be essential the model A. We have to just put that into extract function. Then I'm just going to go ahead to just put the model A. It's going to be my first argument. However, we have another arguments also, for example, for the parse, that's going to be, for example, you specify the parameters that you just want to just, for example, extract the posterior, for example, inference from it. And I should say, we'll keep the rest of, I should say, arguments as a default, which comes with the extract function. And it's going to be all that we need for the extract function to just incorporate the model A as a stand fit class. However, before I just execute that, I'm just going to store the result of that line into an object. I just call that the posterior, which it essentially extracts the inference from the posterior density that we have about the parameters that we are interested to find, and make an inference and the best estimates about that. For example, you remember when, if I just go back to the whiteboard, we had a couple of parameters. We had the A, which we just have it as an alpha in my, I should say, model. We have the B, which is the intercepts, which we just call that as a beta in the stand, and we had the sigma, which we essentially call that at the Z as the sigma itself in the model that we had. Then as a result, I'm just going to just go ahead and execute that line by pressing Control Enter, and I have the object. You can see that as a posterior, which is list of 4 objects which is created there. Okay. And now we can also click on it. You see that, for example, you have, for example, your estimates for the alpha, for the beta, for the sigma, and also we have likelihood, I should say, the LP. We are just going to go back to that in the future tutorials, because we're just going to use that essentially somehow a variant of that for the model comparisons then. And the number 2000 that you see here, it's essentially 4 times 550, 500. Why 500? Because if you just go back to the model that we run, we had, I should say, for example, the iterations of, I should say, 1000, and we had, I should say, 500 as a warm-up. The rest of 5000 multiplied by the 4, it's the thing that this is called, I should say, for 2000. When you just check the posterior, which it says that it's going to be a vector of, I should say, a 2000 components inside. Now that we have this one, then we have created, I should say, the posterior function. Now we just want to just go ahead and check to see that if the model has converged based on, I should say, on the number of the iterations that we had. In order to do that, I'm just going to go ahead and just go for the posterior that I had. I'm just going to go with the $, and I'm just going to pick up, I should say, the alpha, which is going to be, if I execute that line, you see that all the inferences and the best estimates that for each sampling for 2000 times that you had, I should say, for example, you can check the length of the posterior alpha. You see that it's going to just go to the 2000, and you see that there are 2000, I should say, number, which essentially they are their estimates from each sample that Stan algorithm took from the posterior distribution to make the best estimates for the alpha. What was the alpha? Alpha essentially was the slope of the weights that we had. Okay, now I'm just going to go, but essentially in order to just get the alpha, you know that from the things that we have to just take the mean. That's the thing which we're just going to cover that in the next coming tutorials then. Would you not just jump ahead? We are just only here to just check the diagnostics to see that if the Stan model that we created has converged essentially. In order to do that, I'm just going to check back again. After I just check the length, posterior, $, I'm just going to go ahead with the alpha, which is going to be the slope. And now I'm just going to plot it. I'm just going to plot the alpha. However, because I'm just going to do the same thing for beta and the sigma, because I have to check the convergence for all of those parameters. Remember, you have to check the convergence for all the parameters that you just defined it, I should say, in the woman.stan file. If you go back to that file, which is woman.stan, that's the name which I called for my stan file, you see that at the blocks of the parameters, you have 3 blocks. You have real alpha, real beta, and also the real sigma. We have 3 parameters. Then essentially what do we have to do is that we have to check that we have a convergence and stability for all the parameters that we talked about it right now then. Okay, if that's going to be the case, I'm just going to come here and say, okay, I'm just going to plot it, but for each one, then I just go to okay, let me okay, just here, and I'm just going to execute it, and let's see what the plot looks like. However, it looks like the dot. I'm just going to go ahead and I just put the type. I put that equal to, I'm just going to put the L. Let's see what it looks like. And now you see that the plot for the alpha looks like that. And now, however, if we just want to, let's say, for example, just include some other plots, because I just want to just show the convergence for the other, I should say, parameters of my model, then you know that you can just go ahead to just put that, for example, with the MF row, which I said that it's going to be equal to C 1 by 3, because I can see that 3 plots just one into one, I should say, window then okay, that's the thing, that's the convergence which I showed that it's going to be for the alpha. I'm going to follow to do the same thing exactly for the other parameters, which is going to be called the posterior I call the dollar sign posterior, and I put the dollar sign. Now I'm just going to go for the beta, which it was my intercepts, and I'm just going to put the type equal to L in order to show that zigzag type of the plots. I'm just going to execute it. I can also, in order to have a kind of a distinguish that from the other one, I can just come here to call that main. For say, I should say it's going to be for alpha. I'm just going to come here, say that the main, I'm just going to name my plots. Look at that. If I, okay, I have to just put the this one here. If I execute it, let's clear all the plots. You see that when I execute this one, I have the name alpha. Let's plot it. Let's go back again to the par arguments which I had. I'm just going to go with this. It's now you see that the name of the parameter, which is alpha, which it shows that on the top. I did that with the main argument with the plot function. The other one is going to be for the beta. I'm just going to execute this. You see that the other plots is generated just for the parameter beta. But remember, we had also the third parameter in the model that we had, because as I said, and that's very important, you have to check, I should say, your convergence for each individual, I should say, of your parameters. Then now I say that, okay, it's going to be posterior. I'm going to choose, I should say, the other parameter sigma, and I'm just going to go with the type as equal to L to check its convergence. And now I'm just going to name it. I'm just going to go ahead, we just put it as the main equals to, let's say, for example, the sigma, which is going to be the other parameters. Look at that. I have now 3 plots, which I'm just going to zoom on it, and it shows that, okay, for example, the thing which we have, it shows, for example, for each parameter, the alpha, beta, and the sigma, we have kind of a zigzag type of, I should say, the plots, which we see it there. And I should say, in one of the 2 methods of the convergence that we have, one of them, I should say, this is the trace plot that we call that. And also the other one is R statistics. In terms of, I should say, the trace plots, that also we have one other tutorials that we have another package which is called the shiny stand in order to show the diagnostics of the model. But at this stage, we are just, the thing which we're just going to do is that we check at these plots and we said that these models, as long as they are zigzag like that, they are just going to show the convergence. On the next tutorials, when we come back, I'm just going to show you a type of, I should say, methods that it shows that if the model has not converged by one of its parameter, how these plots may look like. And that's going to be the topic of the next tutorials, that when we just come back, we're just going to talk about this then. I see you at the next tutorial, and see you soon then.